Welcome everybody in our second talk. Our second speaker is Professor Stavros Papadakis from the University of Ioannina in Greece, who will talk about combinatorial conjectures and algebraic rules. Stavros?
Let me start. There are two main subjects in the present talk. The first subject is to discuss in the beginning a number of interesting and discrete geometry questions related essentially to F vectors of convex polytopes and simplicial spheres. The second is to introduce the well-known notions of weak left-edge property and strong left-edge property for a graded algebra. And these properties, the motivation for them is that if we prove that the phase ring of a simplicial complex D has any of them, then this has important implications for the F vector of the simplicial complex. So let me start. When we say and write on the slide polytope, we always mean convex polytope, and D polytope, we mean, as it is usual, a convex polytope of dimension D. We recall from previous talks that if we have a convex polytope, the phi of P denotes the number of I faces of P. And similarly, if we have a simplicial complex, Fd, Fi of D denotes the number of I faces of D. The first question, which is to describe, we fix a dimension D, and we would like to describe the set of all F vectors of convex polytopes of dimension D. Then we will say a little more soon. For dimension D of the polytope 2 is easy. For dimension 3, it was solved by Steinitz around 1906. And to the best of my knowledge, for D greater or equal 4 is still an open question. So this is the F vectors in the class of convex polytopes. The second question is to describe the F vectors in the classes of simplicial and simple polytopes. This is obviously a famous and very well-known story. We will say more a little later. And the short description is that there was a conjecture by Macmullen around 1971, which we will describe in detail soon, the g-conjecture. And as it is well known, this was proven around 1980 by Biller, Lee, and Stanley. We will say more details during the talk. The next question, which was open until very recently, was to describe, we fix a dimension, d minus 1, and the question is to describe the set of all possible f vectors of simplicial spheres, which means a simplicial complex with geometric realization homeomorphic to a sphere of that dimension. And this was solved by Karima Di Prasito in 2018. And it was, before that, it was known as the g-conjecture for simplicial spheres. The fourth question, which was known like as a conjecture of Grünbaum, Kalai-Zakaria, was about a bound on the number of d-dimensional d-faces of a simplicial complex that has a PL embedding into the space R2D. PL embedding means that there is a simplicial complex which is a subdivision of D, such that the embedding is linear on each, is affine linear on each simplex of the subdivision. And this, and Kalai in 1991 reduced the conjecture to proving the strong Lefsetz property of phase rings of PL simplicial spheres. And this was proven in a, by Karima Di Prasito in 2018. Is there any question? I don't hear it.
No, that was something going on in the back room, sorry.
Thank you. So we will now say a little about the first question, which is still open in general. The first question was to describe all possible f vectors of convex polytopes of certain dimension, D. If the dimension is 2, we clearly have only n-gons with interior, so we get a very easy description of the set. It will have m vertices and m1 faces. Which describes the set of F vectors of three-dimensional convex polytopes given by the Euler equality and two inequalities. Now, the next step is to describe what was the conjecture, which is now a theorem, for the characterization of the F vectors of simplicial spheres and simplicial polytopes. So, we assume we start with a finite sequence of positive integers, and for convenience, we set f minus 1 equals 1. As was mentioned in previous talks, we defined the h vector, which is a way to package the same information of the f vector, slightly different. And for the first half of the h vector, we define the g vector to be the difference of hp minus hp minus 1. Now, this slide defines the G conditions associated to this D in terms of the H vector and of the G vector. The first condition is the symmetry of the H vector with respect to the middle, D half. And this has appeared in the previous talk. The second condition is that GP are non-negative. And since GP are defined like a difference, this means that up to the middle, the sequence of H is increasing. And due to the dense Somerville, we get that H is a unimodal sequence. Moreover, there is a more complicated part of the conditions, which is written on the slide, which says the following. If we write the integer G, the positive integer GP, positive non-negative integer GP in this form, with these conditions, then the next integer GP plus 1 should be less or equal of this sum, which is obtained by the previous by adding plus 1 on the upper part and on the lower part, and these are the usual binomial coefficients. So these are what we call G conditions. For a given D. Now, the remark is that if we have a pair of positive integers, there exists a unique expression of G of GP in this form with these conditions. And it can very easily be constructed as follows. We choose the maximal integer n such that the binomial coefficient n, or choose P, is less than or equal to G. And then we continue with the smaller pair, P minus 1 and G minus nic choose P. And this is an example when P is 3 and G is 12. I mean, we have that the first is 5, choose 3, because n equals 5 is the greatest integer such that n choose 3 is smaller or equal to 12. An important remark is that this condition, the G conditions, are also called like M vector conditions, and they were originally discovered by Macaulay in the 1920s when studying the growth of the Hilbert function of graded rings. So we have a graded ring, it has graded components, and Macaulay too studied what could be the growth of this function. We will see that these are the conditions that appear on the characterization of F vectors of simplicial polytopes and simplicial spheres. Now, we remark that, as it was already mentioned by Vasiliki, that a convex polytope P is called simplicial if every face of it different from P icosahedron are clearly simplicial polytopes, and as was mentioned in the previous talk, the cube is not a simplicial polytope, and the dodecahedron also is not a simplicial polytope, because cube has a face that's not a simplex, and the same for the dodecahedron. Now we go to the big and important theorem that took almost 50 years from the conjecture to be formulated in this way. And as we said before, it was a conjecture of McMullen around 1971, and then it was proven parts of it by Bilera Lee, Stanley, and Di Prasito. The statement is that a finite sequence of positive integers satisfies the G conditions that were mentioned in the previous slides, if and only if it is the F vector of a simplicial diploid of P, if and only if it is the F vector of a simplicial sphere of dimension d-1. So we get a complete characterization for simplicial polytopes and for simplicial spheres. Let me say a little more about the history of the proof. Bilera and Lee, around 1980, proved by an explicit construction that if a finite sequence F satisfies the G conditions, then there exists a simplicial polytope which has this F vector. So the conditions, the G conditions are sufficient. Now, around the same year, Stanley, in a famous proof, using the Hartleb-Sachs theorem that we will mention later in a form, for the singular cohomology of a projective toric variety associated to P, showed the other directions for simplicial polytopes, that the F vector of a simplicial dipolytope satisfy the G conditions. As I say, the second part of the talk will be about the Lefsetz properties. And then, Adiprazito in 2018 proved that the F vector of a simplicial sphere satisfies the G conditions. Let me remark that we gave with Vaso Vasiliki Petrotou a second proof in 2020 which was based on proving the generic anisotropy of the phase ring of D over any characteristic 2 field K. Now let's discuss a little about the characterization of the F vectors for simple convex polytopes. Now we start with a remark that if we have a vertex of a convex polytope of dimension D, necessarily D is connected by one phase by edges to at least D other vertices. For example, for the tetrahedron, each vertex is connected to 3. The same for the cube, For the octahedron, each vertex is connected to 4 more vertices by edges. And the well-known definition is that we call a convex polytope of dimension d simple if each vertex of it is connected to exactly the other vertices. And it is easy to see that the tetrahedron, cube, and dodecahedron are simple polytope, while the octahedron and the icosahedron are not. We remark that if we have a polytope of dimension d, we can define it in a natural way vector of the polar polytope is the f vector of the original polytope reversed. And one can prove that a polytope P is simplicial if and only if the polar polytope is simple. As a corollary, the characterization of the f vectors of simple polytopes follows from the above characterization of the f vectors of simplicial polytopes. Now an example, as it is well known, the polar of the cube is the octahedron. And we have that the cube is a simple polytope, but not simplicial. And on the other hand, the octahedron is a simplicial polytope, but not simple. And we see that the f vector of the cube is 8, 12, 6. And the f vector of the octahedron is 6, 12, 8. So this finishes like the first part of the talk. It's kind of historical. Are there any questions?
It seems that no.
So now we will describe the Lefsetz properties. Let me go a little back. As was already mentioned, Stanley proved a Lefsetz property for simplicial dipolytopes for a ring associated to P. It wasn't mentioned, but Adiprasito also deduced the g-conjecture from proving strong Lefsetz properties of phase rings. And also the second proof was also proved the generic anisotropy, and then this generic anisotropy implied the Lefsetz properties. So it seems that many important proofs are based on many important results so far are based on proving the Lefsetz properties of certain algebras. So let me start with the original hard Lefsetz theorem, which at least the statement is due to Lefsetz. I don't remember the period, maybe 40s or 50s. Now this is about a very strong property of the cohomology ring of a compact Keller complex manifold. So we assume X is with a metric G is a compact Keller complex manifold without boundary of complex dimension n. The Keller metric, one can think of it like a Riemannian metric with certain properties, compatibilities with a complex structure, and it induces a cohomology class, a non-zero cohomology class in H2 of X with complex coefficients. Then the hard-Lefsetz theorem, which is a deep and very important theorem in complex geometry and algebraic geometry, says that these spaces H upper I and H2n minus I, which we know by Poincaré duality that they have the same dimension, we actually have that the multiplication by the power of this omega, exterior power, is an isomorphism of complex vector spaces. That was the original hard-Lefsetz theorem, and it's in the context of complex geometry. And now we will see the algebraic interpretations of it. So we start with an infinite field, a positive integer, and the polynomial ring in m variables over k, with a degree of all variables equal to 1. And since we will need it, we denote by S the quotient of R by the homogeneous ideal I. We first assume that S has Krull dimension 0. Krull dimension 0, as was mentioned already on previous talks, means exactly that S, this quotient, is a finite dimensional K vector space. So since it is a graded, it has a top degree, which we denote by R. So we have S to be the direct sum of the graded components with indices from 0 to R. And obviously, each graded component is a finite dimensional vector space. So when S has Krull dimension 0, we say that S has the weak Lefsetz property if there exists an element, homogeneous element of degree 1, such that for all I non-negative, the multiplication by omega map from S graded component Si to the next is injective or surjective or both. And we say that S has the strong Lefsetz property if we have what is written on the slide, which means multiplication by there exists omega in S1, which multiplication by this suitable power of omega gives bijections mapped from Si to the symmetric one, SR minus I. So this is the definition of weak Lefsetz property and strong Lefsetz property when we are in Krull dimension 0, which also is also called Artinian case. Now, we recall the important definition that if we have S which has Krull dimension positive, there is the notion of linear system of parameters as written on the slide. So it is is D. Since K is an infinite field by assumption, such a linear system of parameters always exists. And now we will give the definition of the strong and weak Lefsetz property. In the case of Krull dimension greater or equal 1, under the assumption that S is Cohen-Macaulay. And the definition for the weak Lefsetz property is that S has, we say that it has the weak Lefsetz property if there exists a linear system of parameters such that the quotient has the weak Lefsetz property. And moreover, we say that S has the strong Lefsetz property if there exists a linear system of parameters such that the quotient has the strong Lefsetz property. It is clear from the definitions that if S has the strong Lefsetz property, then necessarily S has the weak Lefsetz property. And the converse is not true in general, even for Gorenstein S. Another remark is that it can happen that there is a linear system of parameters that is good. If we divide by it, we get the strong Lefsetz property. While for another linear system of parameters, the quotient may not have the strong Lefsetz property. So it is delicate with respect to the linear system of parameters. In general, in algebra, in commutative algebra, it is, there is a lot of recent research in the last 20 years about these two properties. And somehow the idea behind it is the following. If a class of objects like the simplicial spheres, the phase rings of simplicial spheres, have this property, then first, it's difficult to prove, and second, it implies very good things. So it is desirable to have it because it has lots of implications, either of the two properties. On the other hand, there are many algebras. There are examples of algebras that do not have this property. And often there is a nice geometrical, algebraic, or representation theoretic reason for this failure. And also, so it is usually very useful, and it's a lot of active researches to investigate these properties and find techniques that explain and prove that they have it, or explain when they have it. To go back to more elementary things, it is clear from the definition of strong left-edge property that the dimension should be symmetric with respect to the middle, which means the dimension of the SI, if S has the strong left-edge property, then the dimension of the SI is equal to the dimension of SR minus I. Moreover, as was mentioned before, if S is a Artedian, rule dimension 0, and has the weak left-edge property, then necessarily, for very easy reasons of linear algebra, the sequence of dimensions of the graded parts is unimodal. Unimodal means that there is an n greater or equal to 0, such that up to the point n is weakly increasing, and from n plus 1 and so on is weakly decreasing. And this is also a desirable property, and that many sequences in combinatorics have, but also there are some, like the F vector of convex polytopes, that do not need to be unimodal. So there exists F polytopes with non-unimodal F vector. Then another property is the following. Assume we have an Artinian S, and we have an omega which has the weak left-edge property. This means that the multiplication by omega from SI to SI plus 1 is injective or surjective or both. We set A to be the quotient of S divided by omega. In general, if we don't make any assumption about omega, it is not, the Hilbert function of A can take many values. It's difficult to control the graded parts, the dimensions of the graded parts of the quotient of X, of A. However, but if we assume that omega has this property, then necessarily the dimension of, again for obvious linear algebra reasons, the dimension of the grade AI is the maximum of 0 and the difference of dimensions. So this gives a nice control. This specifies the Hilbert function of A. And this is useful when we want to, when one proves that the weak Lefsetz property implies the G conditions. This is a remark that assume we have a simplicial sphere. It is well known that to prove that the F vector Karim Antiprazito proved the stronger statement that for any infinite field K, the phase ring K of D has the strong Lefsetz property. Let me finish with a unimodality question conjecture by Stanley. I mean, which originally was stated slightly different, but assume we have a standard graded. Standard graded means all variables of degree 1. And it is a Cohen-Macaulay integral domain of Krull dimension D. And we have a linear system of parameters, and we denote by A the quotient. This question conjecture states, which is open, states that the sequence of the dimensions of A, of the graded parts of A, is unimodal. This is a question, this is a conjecture that's open. However, if we replace in the above conjecture the integral domain assumption with the assumption reduced, which means the only nilpotent is 0, then the statement is false. And there are even counterexamples which are phase rings of doubly Cohen-Macaulay simplicial complexes. So let me finish with the references. The first is the 2018 paper of Antiprazito. The second is the paper where Bilera and Lee proved, gave the construction and proved the sufficiency of the G conditions, McMullen's conditions. The third is the well-known book by Bruns and Herzog. The Kalai on this paper is related to the Grünbaum Kalai-Zakaria conjecture. This is the famous paper by Macaulay that introduced the G conditions and proved that they specify the growth of certain Hilbert functions of graded rings. This is the paper which gave this, the next is the paper that gave the second proof of G conjecture using characteristic to anisotropy. The first, this is the paper by Stanley that described his proof using toric geometry and Hart-Lefsetz theorem for the necessity of the G conditions. And the last one is the paper by Steinitz, that's a reference for the result for the complete characterization of the F vector of convex three-dimensional polygons. Thank you for your attention.